Okay, thank you. Looking back, I now want to talk about applications, which were also, to some extent, the motivation to develop these structures. So, what I want to explain here in a way as informal as possible is how these structures are used to construct a three-dimensional topological field theory. Now, topological field theory, despite its name, which sounds like physics, is a very concrete mathematical object. And I could define it here, but I don't want to define it. So I want to present a bit of a simplified version, which is in the spirit of the axioms by Atiyah. So what I want to do is, I want to be able, in particular, starting from this type of input data, to pick some closed-oriented three-manifold and to assign to it a scalar and invariant. Of course, this is an ill-defined question if I'm asking it in this way, because you can simply assign to one length space e to the 2 pi over 17, and to any other non-homomorphic manifold 0, but that's not interesting. So the interesting thing is that you can assign more things to more algebraic quantities to more geometric things. So in particular, we want to be able to assign a vector space to a closed-oriented surface. And it's not just a vector space, but it's fitting a vector space that comes with the action of the mapping class group of the surface. And then given a three-manifold M with boundary, the boundary is such an oriented surface, we want to obtain a specific vector in this boundary, and in the end, there are lots of axioms which ensure, for example, that if you are gluing two pieces of manifold along a common boundary, you're getting a closed manifold, that you can compute the manifold invariance in terms of these vectors. But the basic thing I want to do now is to assign to the two manifold a vector space with an action of the mapping class group, and to a three manifold with boundary the vector. And there is an old construction for this, which has been recently or relatively recently written up in a very useful way. So I'm following here in the formalism this very nice textbook of Serre and Universität, and I'm summarizing a bit the construction. So let's take as the simplest input data the spherical fusion category. So now I'm satisfied. Now take as an oriented three-manifold, possibly with some boundary, and now comes something which is characteristic for this construction, which is a drawback, but which will also produce interesting structure. We fix a skeleton in N. So what is a skeleton? Let me first present you a picture. So a skeleton is additional structure. You can think about it as a generalization of a triangulation. Serre and Universität are using a notion of a skeleton which had been developed by Mathieu, and which had been developed in a way that if you are choosing two different skeleta of one and the same three-manifold, there is a sequence of moves on this skeleton which allow you to get from one skeleton to the other. And this is a hard piece of combinatorial geometry for which I'm completely incompetent. And it's also, by the way, rather during this came from Mathieu's work. So the nice thing is that these moves are compatible with the algebraic structures we have seen in a very deep and non-trivial way. So now let me explain how the construction goes on. So these constructions are also called state sum constructions. What do? We take an object, actually in this formulation, a simple object, and we assign to every phase some simple object in D. if you are worried about simple objects, if parts of the construction can be generalized to a non-semi-simple setting, and then you wouldn't take simple objects in some over isoclasses of simple objects, but this can be formulated in terms of coins. But I don't want to talk about coins now. Yeah, so just to show you, it's more categorical than it looks here. So actually, what you should think about, the way you should think about here the fusion category is that you decide to work with the fusion category as a bimodule category over itself. And there are generalizations where you replace this regular bimodule category by some general bimodule category. But let's go to the simplest case. And let's say what we consider is that to each of these spaces, we assign some simple object, D1, D2, D3, and so on. If we have such a surface which is in on a boundary here, sorry, this was not intended, on sigma we don't assign anything. That is very good. Now, what is the next thing? The next thing is that we observe that we have here edges. If I look at such an edge, then the edges are actually oriented. I can go around counterclockwise. I will encounter several variables, and they are naturally cyclically ordered. Now, I shouldn't have talked about edges, to be honest, but I should have taken half edges. We've seen half edges yesterday. Half edges are pairs consisting of an edge and an endpoint. To such an edge, I'm assigning a vector space. Remember that here I have state some variable D1, D2, D3, and the vector space I'm assigning to this is from D1, tensor D2, tensor D3. It could go on if there are more surfaces incident to the edge into one. And pivotality implied that these home spaces were cyclically invariant. So only the cyclic order of this object matters. So in this way, I get to assign to every half edge, and let's recall what a half. So now an edge, a half gives rise to two half edges. So if there is another vertex here, there will be two half edges. The cyclic order is opposite. These two vector spaces are actually paired. They are paired by the trace. That's why we needed a good theory of traces. And if you have two vector spaces which are non-degenerately paired, well, there's a canonical vector. So what we get in this situation, after having chosen these simple objects assigned to the faces, is for every half edge a vector space. And we tensor all these vector spaces, and this tensor product over all vector spaces, V delta, contains a canonical vector. This vector space can obviously not be some good invariant just for the manifold. It depends on the skeleton you've chosen. Because if you choose a skeleton which has many more faces, the vector spaces will be typically much bigger. Still, it's a finite dimensional vector space. Now, some new ingredient enters here. So what's entering in the next step is the following one. Suppose we have a vertex. Then at this vertex, several of these lines meet. And between these lines, you have faces. The faces are labeled by objects in your monoidal category. I take a small sphere around the vertex, and here this line is then labeled by the corresponding state sum variable. I take a small line, and I do this for all the faces, they cut lines on these little surfaces, and in this way, I'm getting a graph on the surface. I'm getting a graph on the surface, which you see here, and there is now the following thing. We have on spheres a graphical calculus. This was the origin of the word Serre. And this graphical calculus allows me to do the following thing. If I'm given here the vector spaces which came from half edges, and if I have chosen vectors here in these vector spaces, and these are the lines are labeled by these simple objects, then the graphical calculus gives me a way to produce a scalar. So how is this related to a trace? Well, one of the simplest graphs you could imagine on a sphere is just one line and one vertex. And this is now labeled here by something which is an endomorphism. And this endomorphism, and the invariant of this graph is the trace. By the way, that's in parentheses. The fact that the traces are twisted by the Nakayama functor has a natural interpretation in this context. The Nakayama functor should be thought of as an object in some Drinfeld center-like category, in the sense that it comes with some modulo functor structure. And then you should imagine, if you set up a fully fledged graphical calculus, that there is on top of everything, there is a little ray going inside some inner sphere. And this inner sphere, well, we all know the sphere has non-trivial Euler characteristic. So it needs some insertion. And if you go through the formalism, then you see that's exactly where you can have the natural geometric home for the Nakayama functor, and that's the framed TFT reason why traces should be Nakayama twisted. This was just showing you or sketching how these things are related. So what are the steps? So we pick the skeleton, we assign objects to the faces, we get from this a certain finite dimensional vector space which contains a distinguished non-zero vector. It's a non-zero vector because in the end it came from the pairing of the vector space and the dual, and the vector, the canonical vector you have there is obviously non-zero. And now we apply, we have from the graphical calculus, we have a map which allows us to assign to those half edges that are incident to a vertex a number. So in this way, we can evaluate many things except for the edges that never end at the vertex. These are precisely the ones which go to the screening boundary. And we get, in this way, we get here, by applying the evaluation, we get a vector V delta. It depends on the skeleton. It depends on this auxiliary combinatorial structure. In a tensor product which is assigned to these edges which go to the boundary which do not end in any vertices. And this vector, this is what we now want to continue to work with. So what we take is the vector space that is generated by these vectors for all possible labelings of the faces by objects. And this gives a vector space that depends on, no, we take as the external vector space the tensor product over all vector spaces attached to the edges. And inside, we take the vector space that we obtain by all these vectors. And a lot of the work in the book is to show that if you take all these vectors for different three manifolds that have as a boundary sigma, you're spanning a finite dimensional vector space that is independent on the choice of skeleton. And that's the way how this structure assigns to the three manifold with boundary a vector, and to a two manifold an oriented manifold a vector space. So now let me try to generalize this game, and then we will get to something which has actual applications in physics. So let's consider now the case that we consider that we go to a three manifold, which is simply a cylinder over a two manifold. Well, in this case, we can do the following here. We can, this manifold has two boundaries. One boundary is of the type that we have been discussing so far. The other boundary we want to consider just as a boundary where we are imposing boundary condition. Now, there is a long analysis of different levels of rigor, which shows that spherical module categories should be good boundary conditions. Of course, this has a long history, so people were not aware of the condition that the structure that this should be spherical, and part of the theory I've shown you is to get a really well-defined construction. So we needed to develop to this end the spherical, and then not the spherical module category. And now the construction actually generalizes, and in such a situation, again, get a vector space attached to the surface and some triangulation, and you get a vector space that is independent on the triangulation. And one remark I'd like to take is that bi-module categories appear here as well. And I was insisting on module categories. Module categories are assigned to boundaries, but you can generalize boundaries. So if you insist that the manifold continues, then you could have inside the manifold some surface defect, and you could have different spherical categories, D1 and D2. And in this case, we would choose here D1, D2 spherical module category, and we would choose, and the case I was presenting was, in a sense, the special case that this here is vect, and we have just single-sided module categories rather than bi-module categories. So there's an enormous delay now. Okay. Yeah, so let's look at this in a concrete example. And then I will show you how this gives rise to models that have been studied in statistical mechanics. So let's take a surface, sigma. So I've here only drawn part of it. Here we will impose a boundary condition. And then we take a particularly simple a simple skeleton. So here locally it looks like a honeycomb lattice, and the only thing we have here are these additional edges, and of course there are faces here. According to the prescription that I was mentioning, what should we do? We should assign to these blue faces. We should assign simple objects. Simple objects of what? We should assign simple objects here in our spherical diffusion category D. I was just writing D. This starts to be a bit annoying, I think. On the other hand, for these faces here, we assign objects. So capital A is an object in a D in a left module category. So now we mix these structures of model categories and monoid. And then we compute vector spaces. The vector spaces have been obtained by taking such a half and considering that things are cyclically ordered and taking the corresponding home space. And it was cyclically ordered due to the pivotal structures. So here for the half edge I've been indicating, we do not have any problem. But here I have a half edge where two objects in the module category appear. So now I need a structure where I can deal with the module categories, this actually spherical module categories, exactly in the same way as I did it for the monoid category, and that's where the pivotal monitor contexts enter. So I'm using the homes in the pivotal monitor context to get also vector spaces for these type of edges. And if I'm looking at different pairs of half edges, they will be again non-degeneratively paired. They will be non-degeneratively paired by a trace, but the trace is now on a bimodule category, not on a monoidal category. And that's why I had to develop a theory of trace which was on linear categories and not on monoidal categories. So I have these home spaces, and now I have to do this evaluation. So I have to do an evaluation where now A, B, C, they are simple objects in a module category, and alpha, beta, and gamma, they are simple objects in the monoidal category. There is such a graphical calculus which evaluates this, and it evaluates it to something very natural. So if you show to certain people a tetrahedron and you ask what kind of representation theoretic quantity corresponds to a tetrahedron, they will say 6J symbols. And 6J symbol, this exactly matches what we have here, but the simple objects, so the J's, they are partly objects in a monoid category, partly in a module category. There is a graphical calculus for this as well. It was developed in much more generality in a recent PhD thesis, and it indeed assigns to these graph these 6J symbols, which are just the mixed associators we had in the beginning, and recall that the mixed associators were this isomorphism, sorry, let me write it differently, let me write it correctly, which were showing how C1, C2, and N is related to C1 tensor C2 to N. So that were the mixed associators, and which we had on one of our very first slides. And if you are writing down this mixed associators in terms of their actual home spaces, then this is exactly encoded in the value of this graph. So what we get in the end is that if we evaluate such a TRHW01 model on a manifold, we need all the boundary, we need all the structure. What we then did, and this is a bit reverse history, to be honest, is we took these things and we used it to construct what physicists call spin models. Actually, historically, it was the other way around. So Hagemann, Notens, and Cascade, they are physicists in quantum information theory and in Kent, and they showed us their models. And they were saying, this must be somehow close to structure, you know. And we were looking at this actually for 2 days. Lawrence Notens is an extremely brilliant, or back then, extremely brilliant PhD student. Now he's a brilliant postdoc. And he was completely instrumental in realizing this. So what we can do conversely is, if you give me a pivot, such a two-object pivotal bicategory, which amounts to a pivotal fusion category and pivotal bimodules, then we can construct from these things, we can construct such spin models. And how is it done? Well, we take all these 6J symbols, and there now is a whole variety of them. And we use them to construct structure on the following vector spaces that have been that you define. So you take all simple objects in your monoidal category, you're summing over them, you take all home spaces. This is very non-categorical in a sense, but the result will be categorical. Then you do this for the action of one monoidal category on the module category. And you do it for the action of the other monoidal category on the module category. This gives you 3 different vector spaces and lots of tensors on these vector spaces, tensors which are just encoding part of the associators of this spherical fusion category. And then you're forgetting that this comes from such a higher structure, so such a bicategory. You have certain vector spaces, and people in physics have some graphical calculus. So since these vector spaces come with a non-degenerate bilinear form, which actually comes from the trace as we know today, they are identified with values. Actually, if you talk to physicists, they will say these are Hilbert spaces, but it's not really the correct argument, I think. And now you're getting these maps here, and you can produce ground states in the following way. You draw on your surface, you draw some skeleton. Here I've drawn it again in the form of such a honeycomb lattice. And then ignore for the moment, please, ignore this red line. And then you have tensors here. You have here vector spaces. The vector spaces come with bilinear form. You're contracting them. Now, these tensors are really a bit more subtle because there is something in the middle here. So they come really, if you contract them, you get a certain vector at all these vertices. So in this way, if you take them in the corresponding tensor product, you get a vector in your ground state assigned to the surface. And that's what physicists are excited about, because they want to describe some vectors in some physical systems with as few data as possible. And to describe this here, you don't need to describe a vector in a vector space, which is dimension of the vector space attached to this point, to the tensor power of the number of points, but you just need to remember this single tensor. Okay, so now you can complicate matters and use the other bicategory to introduce these lines. You have tensors, you're contracting, you're getting other vectors. So you're getting a game where you're drawing lines on your surface, and by certain configuration of the lines, you're getting vectors. Now, this is a nice way to describe vectors. However, for certain applications, you want to have certain vectors. And some vectors which are easy to describe are maybe difficult to describe if you're choosing a different fusion category, which is Morita equivalent. So if you have Morita equivalent fusion categories, you get equivalent state spaces, but the way you describe this by configurations or lines, that's rather different. The fact that you're getting the same vector spaces, that uses heavily the Morita theory we have developed. So by going from one spherical category to another one, you can simplify the configuration of lines you're using. You can simplify the tensors. They will then insert in their numerical calculation. So this spherical Morita theory gives you a description which gives coordinates that are, in a sense, better applied to describing certain situations. And this is nowadays, this was a paper we wrote in Corona times, and this is nowadays widely used in simulations in quantum information theory, that people are using in Morita context to change the coordinate and to be able to make more efficient computations. So I'm aware that this is a very brief and superficial introduction, and the style is of course different to the first part of the talk, but I wanted to show you one thing, but this is actually very useful. Now, I want to show you another thing and to present you some result from representation theory. And it's not what I'm going to explain by TFT. It's not a new result, but I think it's still interesting to understand it this way. Let's go back to your representation theory class. And you looked at representation, say, of finite groups over the field of complex numbers. Then there is a very interesting quantity, the Frobenius-Schur indicator. And the Frobenius-Schur indicator can be computed from the character table. And it decides whether a certain representation is not isomorphic to its dual, or whether an invariant bilinear form on V, an irreducible representation, is symmetric or antisymmetric. Now, the way you can define this is that you consider the following vector home space. This is V tensor V to 1. This is exactly the home space which in the pivotal category had an operation of this type. And this operation, there was a cyclic invariance. So if I'm doing this twice, then I'm back to the original morphism. So if the object is simple, there's just a single home. The home space is 0 or one-dimensional. If it is one-dimensional, the trace of an endomorphism of order 2 can have 2 values, and that's actually the Frobenius-Schur indicator. Now, there is a generalization of this story. And this goes back to Kashina and Sommerhäuser, and in the context, and Schuh, and in the context of pivotal categories to Nge and Schaumburg. So instead of taking one object, you can take any of them. And you can decide any number L of them. You can turn them around. And you can take L of them to turn them around. Now, suppose we have also here a home where we are not, here we were looking at home V tensor V to 1. So suppose we are looking now here into home V tensor N into X. In order to be able to do our argument, I need to somehow cross these lines. While crossing these lines is a braiding, so X must provide such a braiding. So this is naturally defined if X comes with a half braiding, if X is an element in the transition center. And what these people did is they took this method here, they took its trace, and they got a number. So why is this number interesting, and what properties does this number have? Well, this number, these are 2 integers. Actually, you can extend it to integers. And on pairs of integers, you have an action of SL2Z. Just by 2 by 2 matrices. On the other hand, X is an object in the Trinfeld center. The Trinfeld center of a fusion category has famously the property that if you look at its case 0, you go to the corresponding, you turn it into a vector space by extending scalars, then it comes with an action of the modular group SL2Z. Yeah. So the point is that acting, this descends to the topology ring, and acting on the topology ring with SL2Z on X, and acting with SL2Z on this pair of integers, this intertwines. This is an equivariance, and this is very useful. Actually, this enters into the proof of several famous conjectures, and Peter Schauenberg was using this recently to compute Frobenius-Schur indicators for very, very big groups. So these were symmetric groups with a large number of elements. And so how do you understand it? I mean, the SL2Z seems to be very, very different. In one case, it's the action on pairs of integers, and in one case, it's the action on the topology ring of a modular tensor category. What is the relation between the two? Well, since we now have topological field series by the derived Vero construction on surfaces with boundaries, we can do the following thing. Take a solid torus. Take in this solid torus some line inside, which must be labeled by an object X in the Trinfeld center. And take on the outside of the torus and lines which are labeled by an object in the category itself. And obtain the torus by turning just L, by twisting at the lines, by shifting by L in the cyclically when you glue the torus. Well, so what it means is in the TFT formalism, there is a certain vector space. You can compute what this vector space is. It is actually the home space on which we are acting. And then this here, taking the torus, well, that's taking the trace, but it's taking the trace up to turning. So it's taking the trace exactly after, with the same operator that it corresponds to the Frobenius-Schur indicator. So the invariant of this, this configuration is exactly this equivariant Frobenius-Schur correlator indicator. And now it's clear why this is SL2Z invariant. Because you can cut inside a little torus around the Wilson line, glue it back after some action of the mapping class gradient. You can consider this either as acting on the Wilson line inside or as acting geometrically on the boundary. And it has to produce the same result. And that's the reason for this equivariance. So that's a way how realizing quantities you encounter in representation theory, in TFT terms, explains relations in representation theory that are mysterious otherwise. So I'm now coming to the last part of my talk, and I'm realizing I'm a bit quicker than I should have been. I wanted to show you another approach to constructing parts of the topological field theory, and one of their use. And a couple of things that will appear are kind of reminiscent to what we've seen yesterday. So let's do the following. We have looked at what a pivotal bicategory is. Let's develop another graphical calculus for such a pivotal bicategory. So what's this? I want to set this up as a symmetric monoidal functor. It's a symmetric monoidal functor from a symmetric category of corollas to vector spaces. So vector spaces with tensor product, and I have to explain to you what the corollas are. So the corollas are the following thing. This here is a corolla. So there is a point center of the circle. On the circle, you have a finite number of points. These points on the boundary of the disk are drawing to the center. So everything is finite here, so we are not allowed to have infinitely many of these arrows, and we label it. And we label it in this way that since we have here a byte category, we say that A, B, C are objects in the byte category. Then F, G, so the things that are associated to the lines, these are one morphisms. And then B is a two morphism in the byte category. And it makes sense to draw this as in this circle form, because we have seen that if you start with some if you start with some Hom space of this form, then we have canonical morphisms where we change the order. That's what I explained in the previous talk. And we simply define the space assigned to such a situation where we only have a cyclic order. Like here, we define it simply as the limit, or since these are isomorphisms, as the co-limits of all the spectral spaces. So these are corollas. They are labeled by the structure we have in our byte category. And this joint union of corollas, that's the monoidal operation. And to have a unit, the empty set is also considered as a corolla. Now, what are the morphisms? So let me give you an example what the morphisms are. So the morphisms, this here is one object. It's actually given as the disjoint union, as the tensor product of two corollas. And it should give me a corolla or a disjoint union of corollas. It is given by a disk. It is given by a disk where the boundary configuration of this disk is the target corolla. And here I have shaded areas. And if you look at the boundary of this shaded disk, it has the same boundary configuration as here, and this disk has the same boundary configuration as the disk here. So a morphism in the category of corollas is such a final graph labeled again by byte category. So if I say graph, I implicitly mean that the two patches are also labeled. They are labeled by objects in the byte category. And that defines for me a category if I'm telling you what composition is. And let me tell you what composition is. So if I take this corolla here and I compose it with this corolla, I will take simply this. It has this, the outer boundary is equal to the inner boundary here. So I can insert it. And if I'm inserting this, then I'm getting this composition, and that's again a morphism. So this is a rather simple category you can set up by using your objects in your byte category. And then you will, I want to set up now here a functor, which is a symmetric monoidal functor from corollas to vector spaces. So let me explain this. So here, if you think in terms of categories, then in order to go from such a corolla to some Hom space, which is representing this co-limit, well, you have to choose some datum. So for example, here I've chosen that all this, I can choose that all these arrows are ingoing, and the appropriate configuration will be, I have here H, So so I have here H and then F and then G. But if I had chosen, if I had taken a different choice, then would have decided that these two here, they are outgoing, and these here are ingoing. So I have to choose 2 points. That's called polarization. And then I would get a morphism which has 2 outgoing arrows and which has 1 ingoing arrow. And the wonderful thing about a pivotal category, which you have to check, of course, is that all these home spaces are canonically isomorphic. So that's why assigning a vector space to this is well defined. And in the same way, so what we did essentially is we took these disks and we squeezed them into a rectangle that we can apply usual graphical calculus. You can do the same thing with this here, and then you can compose morphisms in your category, take tensor product, and again, this is well defined. So what we get for a pivotal bicategory in this way is a symmetric monoidal functor from corollas to vector spaces. Okay, so now we use this to construct something global for a compact-oriented surface. And let me take the case of a surface without boundary here. The pictures are unfortunately not quite the same. So look, here I'm now looking at a category of graphs on the surface. P would be boundary values we don't need. The graphs are finite graphs on the surface, and I take them to be labeled by objects in this pivotal bicategory. So such a graph is labeled by taking an object for a patch, by taking a 1 morphism for a line, and for vertices, I take 2 morphisms. And I'm now setting up a functor from graphs to vector spaces. And in this way, I get a system of vector spaces. So I've explained here what the labeling is. So you see that all the data, so the 1 morphisms and the 2 morphisms are, the objects in 1 morphisms are used. And I'm now taking as morphisms in my graph category, such surfaces where I distinguish, I take as morphisms, as generators for morphisms, surfaces where I distinguish such a disk, and the disk should obey some transversality condition for the graph. And now, what I'm doing geometrically is I'm deleting everything that's in the disk, and I'm replacing this by a corolla. We know that the graphical calculus tells us that for any vector space I'm now choosing inside the disk, this allows me to contract the vector spaces to get the new vector space here. So the graphical calculus allows me to say that whenever I take a graph here, I assign to it a vector space, which is the tensor product over all vector spaces for all vertices here. And if I'm doing some contraction on disks, I'm getting a linear map on vector spaces, which is exactly the linear map given by graphical calculus. So think about this as a diagram in vector spaces that is labeled by graphs on the surface. And now we do something very natural. We take the colimit of this diagram. And this is, the colimit is a vector space, and this vector space is what's called in the corresponding condensed matter literature, the string net space. So stringlets are not related to string theory. That's it's called stringlets because there are edges in graphs appearing. That's a very poor reason. And you define this best as the co-limit of this functor on graphs. Now, on any graph, you have the action of the mapping class, of the mapping class group of the surface, or rather first of the diffeomorphism group. And this descends to an action of the mapping class group on the stringlet space. And moreover, you can show that if you take a surface and you glue boundaries together, that then this is nicely compatible with the other structure. And this word for nicely compatible, which can be mathematically recursively defined, is the word of a modular functor. So the upshot is that if you have a good graphical calculus on a pivotal bicategory, you can set up a graphical, you can set up from this functor, a functor from graphs to vector spaces, and the co-limits of these vector spaces are exactly vector spaces with mapping class group actions that are very interesting in different contexts. So this modular functor is so these vector spaces should be the same as the ones you get by the TRHW01 construction. If I say should be the same, it is proven by empirical at the level of vector spaces. It's not proven at the level of actions of the mapping class. So there's a problem here. And still, I think nobody expects that this will go wrong, but I'm not aware of a proof that includes the action of the mapping class group. So what we have here is now we have a way to, given a pivotal bicategory, to assign to every surface some vector space which carries action of the mapping class group. And now I want to explain to you how this can be used to describe to ensure the existence of consistent correlation functions in a quantum field theory. And now I have to do a lot of hand waving, but I want to insist that everything here amounts to non-trivial proofs. So let me first say what I want to do. I take a surface that's in this case, this is an oriented surface, compact oriented surface, and this surface can have a lot of other structure. So it can have the type of structure we have just seen, and the physical slang would be that there is a conformal field theory of some type called blue in on this 2 patch. There's some of some other type called green on this patch, and they might be separated by some line defects. The line defects come with types, and these line defects can also join or split, and moreover, there can be boundaries. And it is known for a long time that in the CFT, this decoration data should be. So what they should be is the following. The first thing is we fix C a modular tensor category. What is a modular tensor category? It is a braided monoidal category. The braiding will not be very essential in a moment for the first part here. And then we can construct from inside such a category, we can construct the following 2 categories. That's by category. Let me call it Prof C. So the objects of Prof C are Frobenius algebras. The objects are not just any Frobenius algebras, but they are symmetric Frobenius algebras which have a separability property. So Frobenius algebras come with a co-product, and the co-product has to be an inverse to the product. so assigned to every to every two patch is a Frobenius algebra. These lines here, they are labeled by bimodules, and these are certain bimodule morphisms. So what we have here is a surface with a graph that is labeled by this bicategory from C, and from C turns out to be a pivotal bicategory. What can we do with a pivotal bicategory? We can do the stringlet construction. Well, if you do this stringlet construction, you're getting a vector space, but if you remember how it is done, then this vector space is really something like the free vector space generated by this graphs, not the relations that come from disks. So every graph on sigma induces a vector in this vector space. So what we do is we translate this quantum field theoretic data into a vector in this vector space, which is created from this bicategorical stringlet construction. Why? And you'll see in a moment why we do this. Now, in this context, there is another pivotal Frobenius pivotal bicategory. Namely, we can take a one-object bicategory, which has just our modular tensor categories as endomorphisms. This is also a pivotal bicategory, and there is an obvious functor between these two, which takes, for example, a bimodule and forgets the bimodule structure and takes it just as an object. Well, this functor here is a functor between two categories, but it's not a pseudo functor. It's a functor of a very interesting type. It is what's called a Frobenius monoidal functor. So let me explain what a Frobenius monoidal functor is. If you have a weak monoidal functor, and you know that if you apply to the one object category, you're getting an algebra monoid. If you have an monoidal functor, then if you apply to a one object category, you get the co-algebra. So now such a Frobenius monoidal functor, it is monoidal, that it has a weak monoidal structure. It has a weak monoidal structure, but we do not require that the monoidal structure and the monoidal structure are inverses. This is a structure which might look strange. Of course, we require a compatibility between the monoidal structure and the monoidal structure. I'm not going to write this down for you because you've seen too many formulae already. I'm characterizing what type of compatibility it is. If you consider a Frobenius monoidal functor from the one-point category into a monoidal category, then its image is a Frobenius algebra. That's the point. So, and it turns out that this functor is a Frobenius monoidal functor. And then you do some hard work and you try to show that the graphical calculus is invariant under Frobenius monoidal functors. The graphical calculus is invariant under ordinary pseudo functors. That's not hard to show. And you fail. The graphical calculus is not invariant. But there is a way to repair it. There is a way to repair it, namely, what we have to do is where formerly we had here two patches that were labeled by objects in this pivotal bicategory, we have to take these patches and label them by some triangulations where the edges of the triangulation are labeled by a Frobenius algebra. It's a famous fact that the moves for changing a triangulation on a surface and the axioms of a Frobenius algebra match. So we don't care how we are triangulating, provided the triangulation is fine. And then we apply to this new configuration here, we apply a different string net construction, namely the string net construction for this pivotal bicategory. And now the Frobenius functor is strong enough to provide us here with a vector in, so first with a map from, let me write this here. It is a map from the string net space for the pivotal bicategory for D of sigma to string net space to this delooping is one object bicategory for sigma. And remember that this V itself, this was a vector Vs. This was a vector in here. So this map, which we construct, this provides here a vector ultimately in this string net space. So what is the importance of this? This string net space is the vector space which is expected to be isomorphic as a representation of the vector space that's applied to the TRHW01 construction. What we can show here is that this vector is invariant under the action of the mapping class group, and if you're assuming vectors surfaces, then the vectors are mapped to each other. So if the modular functor would be equivalent in a way described in the book of Bakalov and Kirillov to some complex analytic functor, we would have found here a section in a vector bundle that is invariant under the mapping class group. So it's a global section that's compatible with factorization, and that would describe some correlation function in CFT. What you can do here in this formalism is assuming the equivalence of these two notions of modular functors to show that such consistent systems of vectors exist, and you can compute certain of their aspects. So you can, for example, compute partition functions and show that they are invariant under the mapping class group. So you have modular invariant partition functions. And this is an approach which has the potential to go beyond here to this case where we have actually semi-simple modular categories because we are working in a purely two-dimensional setting. What I look at is we have a recent result that this morphism here is always an iso of vector spaces. So that's kind of interesting, and maybe that links a bit to talks we will have this afternoon. What we would expect is that if you take, if you have a one object category, there's a way to complete it. So if you are given an algebra, this is a one object category, and one natural way to complete it, well, in a semi-simple setting, people would say idempotent completion, but maybe we want to say that the category of representations should be a completion. And what you see here is that if you're in this pivotal setting with Frobenius algebras, this completion doesn't change the vector spaces you're constructing. And that's then this fact that this is an isomorphism is not so strained. And then the techniques to prove it use typically enough Frobenius type structures. So if I'm terribly oversimplifying, there's a famous proof that in a rigid category, any morphism of a Frobenius algebra is invertible. And this is kind of a generalization, just to give you an idea what's going on. Yeah, what's happening here? Why is this interesting? if you're interested in quantum field theory. Take two different such surfaces with different decoration. When we constructed this stringlet space here, we took a quotient, we took a huge quotient. So it can happen, and it does happen, and it happens frequently, that different geometric configurations give the same vector. Here, since our vectors here, which describe correlators, factor through this construction, these different geometric configurations will give rise to identical correlation functions, and you will not be able to distinguish them by just studying correlation functions. So anything that goes to the same vector in this big quotient space which we have constructed from the graphical calculus of pivotal bicategories will be physically undistinguishable by any measurement of correlation functions. This is not so strange in the end because, should I finish? Yeah, good. Yeah, because we know that, for example, topological detected lines have this property, and but they are more interesting in fact, and in particular, it gives you a nice insight how you should define mapping class groups for surfaces which have this type of stratification. We define them as stabilizers of the corresponding vector in the stringlet space, and then they are very big. Udi, are you not happy? Okay, yeah, so there are more things. So we have used actually this pivotal bicategories and the pivotal Morita context to give a Morita invariant formulation of state sum constructions. Next week, those of you who are here next week, they can hear a talk about what is going on if you drop the requirement that categories are rigid and replace it by a Vika duality structure. So Simon will give a talk on this. This is very interesting, and it's very relevant because the representation categories of vertex algebra, which are the natural input, they are not rigid. So rigid is a simplification which I took all the time. Pivotal can be defined beyond rigidity. And this afternoon, there will be two nice talks where we will see parts, similar structures appearing, but in higher dimensions. So that's two of the three talks this afternoon, to which I'm looking forward. Thank you.
Thank you. Questions? Your pictures just now remind me of something in the area of cluster algebras, where people take a marked surface and they construct a cluster algebra where the clusters correspond to triangulations, and you have mutations given by flipping edges, and there are various other things as well. You can construct a quiver out of that and get a cluster category and so forth. Is there any connection between that and what you're doing?
Well, since you kindly asked the question whether there's any connection, I would say what's going on and what's appearing in both contexts is that you have a geometric structure which you have under control to the extent that you know, for example, what are the flips you have between different triangulations, and this has an algebraic counterpart. And then you can use this to do constructions also which are taking something that's locally defined and assign something to surfaces. I'm not sure I can tell you that if you go from final tensor categories to this setup and you're embedding it in this way, then the two constructions should be the same. But definitely it's part of these things where some aspect of discrete geometry plays very nicely together with algebra as well. And of course, that's always extremely interesting.
The TP construction described, and you use it in the data and also symbol, you look like
For some of the aspects, yes. So if, for example, we can construct the vector spaces associated to surfaces, including surfaces that now have specifications that are labeled by finite categories and on the side. This construction is worked out explicitly only in the breakpoints because having the pivotality would have added back then too much, would have required too many things which we didn't have developed. As you know, the next challenge is to extend this to 3 dimensions, and that's not yet investigated. But of course, tracing as much as possible in terms of modified trace as first. Yeah. But I'm pretty sure that once we will talk about one framework we can extend to the 3rd dimension.
again.
You are going to be far.
Any more questions? And if not, then I think